Propose a mechanism for the following acetal formation. If you recall from Gen Chem, when you take methanol and you mix it with sulfuric acid, you have acid-base chemistry that happens. So methanol and sulfuric acid. And the base extracts proton from the acid, putting the electrons back onto oxygen, and that gives you a methoxide. I'm sorry, not methoxide. It gives you an oxonium ion. This is an oxonium ion, and the conjugate base so in other words, when you take methanol and you put it in sulfuric acid, you're basically making this oxonium ion. This oxonium ion is what behaves as the acid in this reaction, and the first step in the acetal formation, the oxygen of the carbonyl will extract proton from this oxonium, putting electrons back onto oxygen, generating a methanol. So step 1 happens. You get this. In the next step, you have a methanol, or you have your nucleophile that's going to attack the electrophilic carbon. So, is it going to be methanol attacking here? Or will it be this oxygen that's within the molecule? So in other words, is an intermolecular reaction going to happen first, or an intramolecular? And the answer is intramolecular will happen first. So and you get the following. Oxonium ion, then the methanol will extract the proton, deprotonation, putting the electrons back onto oxygen, and you get, this is step 2, step 3. At this point, you have what is known as a hemiacetal. This is your hemiacetal. How do you know? Well, this carbon is a carbonyl. This carbon has one OH group and one OR group. So it's a hemiacetal. We're halfway there. Next, we want this water to leave. So this water is what's going to become protonated next from the methoxide. Or, I'm sorry, from the oxonium. And you get step 4. This is step 4. Now these electrons on this oxygen can come down and push this water off the molecule. And that's step 5. Double bond with a positive charge here. If I were to show a resonance of this and put these electrons back onto oxygen, it would look like this. And the positive charge would be there. So whether you chose to show this resonance or directly, the methanol will attack this carbon in either case, and you get oxonium. Next, the methanol will deprotonate this. And you get your acetal. This is step 6. Step 7. This reaction will always occur in 7 steps. Propose a mechanism for the following acetal hydrolysis. Acetal hydrolysis is basically when you have an acetal and you're hydrolyzing it back to its aldehyde, which is the opposite of acetal formation, in which case you take an aldehyde and you make an acetal. So in order to do this, we just treat the acetal with H3O+. How does the mechanism go? Well, we have a hydronium here, and basically we want to protonate first whatever we want to leave. In this case, we want this OCH3 to leave. You don't see it in your product. So, acid-base chemistry. And you get your oxonium. Next, these electrons on this oxygen will come down and kick off this leaving group. This guy, you can make a resonance of it, putting these electrons back onto oxygen. Double-headed arrow for resonance. And you can see that this carbon here is positively charged. It's electrophilic. So in the next step, water attacks the electrophilic carbon. Whether you show it attacking there, or whether you show it on this resonance form, it doesn't really matter. And you get your oxonium. Next, you're going to deprotonate this oxonium. So that will be done by water. And now you have your hemiacetal. That means you're halfway there. This carbon, which is this carbon here, of the carbonyl, has an OH and an OR group. That's why you know it's a hemiacetal. So if we were to label number of steps, 1, 2, 3, 4. Next, basically we want this guy to leave, so we're going to protonate this next. So we got hydronium in the solution. And this guy will take it, the proton, put the electrons back onto oxygen. Next, the electrons on this oxygen will come down and kick off this leaving group, putting these electrons back onto oxygen. And you get next, water will deprotonate this, and you get your acetal. So step 5, 6, 7. As you can tell, acetal hydrolysis is 7 steps, and in the previous example, we saw that acetal formation is also 7 steps. Go figure. So, no matter what, it's going to always be 7 steps, forward and backwards, and if you're missing a step, then you might want to fix that. When you react a grignard with aldehyde, you get a secondary alcohol, unless that aldehyde happens to be the simplest aldehyde possible, which is formaldehyde. In that case, you get a primary alcohol. If the grignard reacts with a ketone, you get a tertiary alcohol. If a grignard reacts with oxyrane, which is your simplest epoxide, you get a primary alcohol, and in which case you add 2 carbons, basically, because oxyrane is made of 2 carbons. Whereas, and also I forgot to mention, in the primary alcohol, when you react it with a grignard, you're basically adding one carbon to that nucleophile. You have an electrophile of one carbon. In this case, you have an electrophile of two carbons, oxyrane. So, grignard reacting with an epoxide that's di-substituted, as in an epoxide that has two R groups off one of the carbons, then you can imagine like an oxyrane with two methyl groups, for example, then you get a tertiary alcohol. And if you react grignard with a epoxide that's mono-substituted, you get a secondary alcohol. In all cases, after the grignard reacts with whether it's epoxide or ketone or aldehyde, you always do a protic workup as a second step. So let's see some examples. In the first example, we're reacting a grignard reagent with the formaldehyde. And if you recall, grignard plus formaldehyde gives you a primary alcohol. So let's see mechanistically how that works. So this carbon that's attached to the magnesium, which is a metal, is nucleophilic. And so the electrons will come and attack this electrophilic carbon of the carbonyl, pushing these electrons up, and you get, so dot on the nucleophilic carbon, dot on the electrophilic carbon. They are now connected to one another. This electrophilic carbon is connected to hydrogen, and an O- now, oxygen. Now the next step, basically when you do your protic workup, you get an alcohol. And this is a primary alcohol. Next one, you're reacting a grignard with a aldehyde, in this case benzaldehyde. So same deal, this is the carbon attached to magnesium, so that's the nucleophile. The electrons come out, attack the carbon of the carbonyl, which is electrophilic, and you get, so I'll draw this exact same thing here. And this carbon, which is the nucleophile, is now attached to this carbon, which is the electrophile. The electrophilic carbon, this carbon, has a hydrogen, a phenyl, which is this benzene, and a O-. After the protic workup, you get a secondary alcohol. Next one, a grignard reacting with a ketone, in this case a cyclohexanone. Same mechanism, electrons come out, attack the carbon of the carbonyl, and you get connectivity between the nucleophilic carbon and the electrophilic carbon. And this carbon is the carbon of the ring, and it has also an O-. After the protic workup, and you get a tertiary alcohol. Next one, a grignard reacting with an oxyrane. And oxyrane is basically your simplest epoxide. So this electrons come out and will open the epoxide, either one, it doesn't really matter, it's symmetrical. And you have a connectivity between the nucleophilic carbon and the electrophilic carbon. So I'll draw the same thing here. And this carbon is no longer attached to oxygen, it's attached to another carbon, which is attached to oxygen. So after the protic workup, you get your primary alcohol. And as suggested before, you basically added to this nucleophile 2 carbons total and ended up with a primary alcohol. So epoxide or oxyrane reacting with a grignard makes a primary alcohol with a 2 carbon addition. So one thing important to mention, none of these O- are just like that. they actually have a counter ion that will be MgBr plus in all cases, something I forgot to mention. Next, so this nucleophilic carbon, these electrons will come out and it'll actually open the epoxide from the less substituted side, this side here, as opposed to the more substituted side here. That's not the side it opens on. So this is the electrophile, that's the nucleophilic carbon. Nucleophilic carbon attached to the electrophilic carbon. Electrophilic carbon is no longer attached to the oxygen, it's attached to another carbon, and that carbon is attached to an oxygen and another carbon. Once you do the protic workup, H3O plus, you're going to get secondary alcohol. So this is a mono-substituted epoxide, and as indicated before, griginard reacting with a mono-substituted epoxide gives you a secondary alcohol. Next, this is a di-substituted epoxide, and we're reacting with a griginard, and what we should expect is griginard reacting with a epoxide that's di-substituted, a tertiary alcohol. So let's see. This carbon, is the nucleophile, so these electrons come out and they will open the epoxide from the less substituted side. So nucleophile is attached to the electrophile. This carbon is now no longer attached to oxygen, it's attached to another carbon that has two methyl groups and an O minus. In this example, we are told to make this product using these available starting materials. Now, this is a secondary alcohol product that we have, and from our little chart here, you can see that to make a secondary alcohol, you can either react griginard with an aldehyde or a griginard with a epoxide that's mono-substituted. So let's try the epoxide. How can I turn this alkene into an epoxide? Simply by reacting with a peroxy acid. So that's a peroxy acid. When you do this reaction, it turns the alkene into an epoxide. Now we want to turn this into a griginard, because basically we're going to do a epoxide opening, a griginard mediated epoxide opening. So let's turn this into a griginard. And next, the electrons here, this carbon is nucleophilic, remember it's connected to the metal, so the carbon that's directly connected to the metal is nucleophilic. These electrons will come out and it'll open the epoxide from the less substituted side. So now there's a connectivity between these two carbons, so I will draw the exact same thing as this here. And this carbon is now connected to that carbon. This carbon is now also connected to this carbon. This carbon has an oxygen, O minus, and it has two more carbons. Okay, now we must do a protic workup to get to our product. So we use hydronium. And you get your product. In these reactions, you have a cuprate and you have an alkyl halide. Simply, to write the product, you take the carbon that's attached directly to the organocuprate, this carbon, and it will now have a connectivity to this carbon. So I will draw this electrophile right here, as is, and replace the bromine with this R group. So this carbon is attached to this carbon. This carbon has a CH2 and a CH3 attached to it. Next, same idea, the Cu, the metal that's connected to this carbon, so we know the connectivity will be between this carbon and this carbon, so I will draw this as such. Now the connectivity is between this carbon and this carbon. Now this carbon is connected to 3 more carbons. 1, 2, 3. Same idea, this carbon will be connected to this carbon that's directly connected to the Cu, the metal. So I will draw this. So this carbon is going to have a connectivity to this carbon. This carbon has a CH2, or a CH, double bond, and 1 more carbon. 1, 2, 3. These are all known as coupling reactions. Primary amine reacting with a ketone or aldehyde makes an imine, whereas a secondary amine reacting with a ketone or aldehyde makes an enamine. Let us consider the following examples. Here we have a ketone, and it's reacting in this first reaction with a secondary amine. So our product should be an enamine. The product looks, for this reaction, something like this. Now you may be wondering, why did I draw the double bond on this side as opposed to this side? Because the double bond forms on the less hindered side. In this example, we are reacting the ketone with the primary amine. So your product is an imine. The imine product in this example looks like this. Whatever comes with the primary amine, whatever R group is attached, it could be an OH, it could be a phenyl, any R group, it just comes along for the ride. In this example, we have a ketone reacting with a secondary amine. So our product is going to be an enamine. I will draw the product. It looks something like this. And the double bond forms on this side. You might be wondering why. Because this side, firstly, is less hindered. Secondly, in order for the double bond to form, a proton must be extracted. There are no protons on this carbon. Thus the double bond can't form on that side no matter what. The next example, ketone reacting with a primary amine. And keep in mind, all of these reactions happen in a little bit of acid, just a tiny little bit. So in this example, my product should be an imine. It looks something like this. Nitrogen, and whatever R group comes with the primary amine is attached. In these reactions, we're reacting a alkene with a CH2I2 and zinc copper. And so these reactions, as you can see, these are the same reagents. You're basically going through, you can just imagine that this I2 is going to leave. You're making a carbene that's going to look something like this. I2 left and CH2 is left. You got your carbene, and that carbene is going to be attached to both. This carbon will be attached to both of these carbons. So your product will look like this. So in this case, alkene, like I said, CH2I2 and zinc copper, you're basically going through the carbene, and so it'll be attached. In this case, we got a bromoform, CBr3H, and we have a base, tert-butoxide. So tert-butoxide will, so in this case, basically, you're going to deprotonate this, and somewhere in the mechanism there, you're going to basically make a carbene that looks like this. Carbon with 2 bromines. So that's what will be attached to these 2 carbons here. So your product will look like this. And these are all cyclopropanes. Three member rings right there. See that? Here we're discussing a Wittig reaction. In order for a Wittig reaction to happen, you need to first make your Wittig reagent, your Ylide, Y-L-I-D-E, Ylide. So that's a 2-step process, and the first step to make your Ylide is an SN2 reaction. So you have your triphenylphosphine, and you want to first do an SN2 reaction with this. So let's see what the products of these reactions are. The second step of the Ylide formation is treating whatever after the SN2 reaction happens with a strong base to deprotonate, forming your Ylide. So let's do step 1. Can we do this SN2 reaction here? Can you do this? Electrons come out. No. Because this vinyl bromide, this carbon that is attached to the bromine, is sp2 hybridized. This is sp2 hybridized. And in order for a reaction, SN2 reaction to happen, you have to be sp3 hybridized. So this is a no reaction. What about in this case? Can I do, this comes down and kicks it off? No, because SN2 reactions only happen on methyl carbons, primary and secondary, never on tertiary. So this is also a no reaction. What about in this case? Well, this benzylic carbon here is sp3 hybridized and it's primary, so yeah, you can do an SN2 reaction there. So your product looks attached to this carbon is now attached to a phosphate. That phosphate is attached to 3 rings, 3 phenyl rings, and it's got a positive charge. Now the step 2, the butyllithium, this is a strong base, and it's going to extract an acidic proton. And the acidic proton is found on the carbon that's attached to the phosphorus. So this carbon has 2 acidic protons in this case, so the base will extract the acidic proton and put the electrons on carbon, back onto this carbon here, and you get this. So this is your Ylide. There's a charge separation there. What about in this example? Well, can you do SN2 reaction like this? Well, this is a sp3 hybridized, so we're good. And it's secondary, and you can do SN2 on that secondary. So yeah, that can do an SN2 reaction. And this carbon is now attached to a phosphorus. So there's a phosphorus. And it has 3 rings, 3 phenyl rings. It's got a positive charge. And the second step, the base, remove this acidic proton, put the electrons on the carbon, and you get your Ylide. pH and negative charge on this carbon and positive on the phosphorus, and you get your Ylide. So what can we do in a Wittig reaction? Well, when you react a Ylide with a carbonyl that's aldehyde or ketone, for example, in those cases, aldehyde or ketone plus a Ylide will do a Wittig reaction to form an alkene. Now, if your Ylide is not stabilized by resonance, then you form your Z-alkene. and in this case we have a Z product. So how can we form this product from this starting material here? Well, thinking retrosynthetically, we need to basically make a Wittig reagent. So what is the yelid that we used? Well, it's this part right here, because that's the part that displaced the oxygen here. So what was that? What did that look like? So this carbon was attached to a phosphorus that had 3 phenols on it and a positive charge. That's your yelid. So this yelid came from, so what was the last step to forming the Wittig reagent? Well, I should do the retrosynthetic arrow. I used a strong base to extract the proton. So this hydrogen, oh, that's ugly. And I used a butyl lithium on this thing to get to here. Now if I take this Wittig reagent and I reacted it, oops, we forgot one last step. What was the first step in the Wittig reagent formation? It's an SN2 reaction. So what was the substrate and what was the nucleophile? What was the electrophile and nucleophile? So let's see. So you always start with your triphenylphosphine. And this part here, because obviously this is a nucleophile, this carbon here is the electrophile. So this carbon with a good leaving group and this ring and everything else that comes with it did an SN2 reaction like this. Now, is that allowed? Well, this carbon here is sp3 hybridized, and it's primary. So, actually, yeah, it's primary. So, yes, it is allowed. This is an SN2 reaction that happened. So these guys reacted to form this right here. Okay,